Equation of motion of stiffness coupled system of two pendulums. Consider a coupled system of two identical pendulums, each having a pendulum bob of mass m, suspended by a light weightless rigid rod of length L. The bobs are connected by a light spring. The bobs are connected by a light spring of stiffness S, whose normal length is equal to the distance between the bobs when none of the two pendulum is displaced from its equilibrium position. Such pendulum are known as stiffness coupled. Okay. Let the two pendulum A and B be set into vibration with a small amplitude in the plane of the paper, and let x and y be the displacement. In same direction of the pendulums marked by A and B respectively, as shown this figure. Okay. Then the spring is elongated by a length x minus y, and the ending to bring the bobs of the pendulum back to its mean position, and due to gravity, ending the bring bobs of pendulum back its mean position is minus mgx by L for pendulum A. And equal to minus mgy by L for the pendulum B. Okay. Then the equation of motion for the pendulum A and B are respectively m double differentiate of x equal to minus mg x by L minus s minus y. Okay. And m double differentiate of y equal to minus mg y by L plus s x minus y. That is x minus y. This is the equation number first, and this is the equation number second. And this is the equation number second. And the first term in each equation is the normal simple harmonic motion terms, and the second terms is due to the coupling of the spring if x is greater than y. If x is greater than y, the spring is extended beyond its normal length, and we therefore apply a force against the acceleration of x, but in favor of the acceleration of y. And dividing equation number 1 by 2 and by m, and substituting and dividing equation number first and second by m, and substituting substituting G by L equal to omega naught square, we have double differentiate of x equal to double differentiate of x plus G by L into x equal to double differentiate of x plus omega naught square x equal to minus s by m x minus y. That is equation number 3. And double differentiate of y plus G by L y equal to double differentiate of y plus omega naught square y equal to minus s by m y minus x. This is equation number 4. Okay. Addition 3 and 4 we get 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 double differentiate of x plus double differentiate of y plus G by L x plus y equal to double differentiate of x plus double differentiate of y plus omega naught square x plus y equal to 0. Okay. Subtracting 4 from 3 we get this is equation number 5. Subtracting 4 from 3 we get double differentiate of x minus double differentiate of y, double differentiate of x minus double differentiate of y plus G by L x minus y equal to double differentiate of x minus double differentiate of y plus omega naught square plus 2s by m x minus y equal to 0. This is equation number 6. This is equation number 6. Equation number 6. Let us choose two new coordinates x and y. Show that capital X equal to x plus y and capital Y equal to x minus y, and double differentiate of capital X equal to differentiate of x plus differentiate of y and single differentiate, and differentiate of y equal to differentiate of x minus differentiate of y, and double differentiate of x equal to double differentiate of small x plus double differentiate of small y, and double differentiate of capital Y equal to double differentiate of small x minus double differentiate of small y. Substituting the value 4 and 5 and 6 we get substituting the values in 5 and 6 we get 5 and 6 we get 5 and substituting the value 5 and 6 we get 5 and 6 we get double differentiate of capital X plus G by L x equal to double differentiate of capital X plus omega naught square x equal to 0. This is equation number 7. And double differentiate of y plus G by L plus 2s by m into y multiplied by y is equal to double differentiate of y plus omega net square plus 2s by m into multiplied by y equal to 0. This is equation number 8. This is equation number 8. Okay. Normal coordinates. Normal coordinates. Normal coordinates. Normal coordinates. Okay. It is seen that where is equation number 5 and 6, it have two variables. We find that equation 7 and 8 have only one variable. The motion of coupled system is thus described in terms of two coordinates x and y. Each equation of motion is a linear differential equation of a simple harmonic oscillator with constant coefficient with only one variable. The coordinates x and y are therefore normal coordinates of the coupled systems. Okay, and thus the coupled system of two simple pendulum has two normal modes, one described by normal coordinates x and the other by normal coordinates y in phase mode. In phase mode. In phase mode. Y equal to 0 when normal coordinates y equal to 0, then x minus y equal to 0 is that x equal to y for all times. For all times the motion is completely described by double differentiate of x plus g by l capital X equal to double differentiate of x plus omega naught square x equal to 0. As the relative displacement of the two pendulum always remains the same and x equal to y, the stiffness of the coupled has no effect. Okay? As the relative displacement of two pendulum always remains the same, is x equal to y, then the stiffness of the coupling, stiffness of the coupling has no effect. Okay, the spring always remains at its normal length. The frequency of oscillation is the same as that of either pendulum in isolation. Okay, the frequency of oscillation is the same. The spring always remains at its normal length. The spring always remains at its normal length. The frequency of oscillation is the frequency of oscillation is the same as that of either pendulum in isolation. Pendulum in isolation is that omega naught square equal to g by l. Both pendulum are always swinging in the same phase. Such a variation are called in phase variation. Both pendulum are always swinging. Both pendulum are always swinging. Always swinging in the same phase. swinging in the same phase. Such vibration are called such vibration such vibrations are called such vibrations are called in phase vibrations. In phase vibrations and the corresponding mode is known as in phase mode, and the corresponding mode is known as in phase mode. Okay, next, out of phase mode. Out of phase mode. Out of phase mode. Out of phase mode. Okay, out of phase mode. If capital X equal to 0, out of phase mode. If capital X equal to 0, when normal coordinates capital X equal to 0, then X plus Y equal to 0 or X equal to minus Y. Okay, for all times the motion of completely described by double differentiate of Y plus G by L plus 2S by M into Y equal to double differentiate of Y omega naught square plus 2S by M into capital Y equal to 0. Okay, then when the displacement x of the pendulum A is position that B, Y is negative but equal to that of A equal to x minus Y. When the displacement x of the pendulum A is position of pendulum A is position that of B Y is negative but equal to that of A x equal to minus Y. At zero displacement, the two pendulum will be moving in opposite direction. Thus, the period motion of the two pendulum will be 180 out of phase. At zero displacement, the two pendulum at zero displacement, the two pendulum will be moving in opposition direction. Will be moving in opposite directions. Thus, the periodic motion of the two pendulum. Thus, the periodic motion of two pendulum thus the periodic motion of two pendulum will be 180 degree out of phase. 180 degree out of phase. 180 degree out of phase. Okay, and 180 degree out of phase. Such vibration are called out of phase vibration. Such vibrations are called out of phase, out of phase vibration, out of phase vibration, and corresponding mode is known as out of phase mode, and corresponding mode is known as out of phase mode, out of phase mode, out of phase mode, out of phase mode. Okay, corresponding mode is known as out of phase mode. Okay, thanks. Total energy of two identical stiffness coupled pendulums. Total energy of two identical stiffness coupled pendulums. Okay. The equation of motion of a stiffness coupled system of two identical pendulum A and B is given by double differentiate of x plus omega naught square capital X equal to 0. This is equation number first. And double differentiate of y plus omega naught square plus 2s by m multiplied by y is equal to 0. This is equation number 2. This is equation number 2. Okay, where capital X equal to small x plus y and capital Y equal to small x minus y are the normal coordinates of the system. X and y are the displacement. X and y are the displacement, the same direction of the pendulum A and B respectively as shown in previous figure, and omega naught square equal to G by L, where L is the length of the pendulum. Okay, length of the pendulum, and omega naught square equal to G by L, where L is the length of pendulum, where L is the length of a pendulum, length of a pendulum. Okay, and S is the stiffness, and S is the stiffness constant, stiffness constant. Okay, and stiffness constant. Okay, and solving equation first and second we get by solving equation first and second we get capital X equal to small x plus y equal to x naught cos omega 1t minus phi 1. Okay, and capital Y equal to x minus y, that is y naught cos omega 2t minus phi 2. This is equation number 3. This is equation number 3, and this is equation number 4. X naught and y naught, x naught and y naught are the normal mode amplitude, are the normal mode amplitudes, and omega 1 equal to omega naught equal to G by L power 1 by 2, and omega 2 equal to omega naught square plus 2s by m power 1 by 2 equal to G by L plus 2s by m power 1 by 2 are normal mode frequencies, are normal mode frequencies. Okay, x equal to x plus y equal to x naught cos omega 1 t minus phi 1. This is equation number 3. Y equal to x minus y, and y naught cos omega 2 t minus phi 2. Equation number 4. X x naught and y naught are the normal mode of amplitude, and omega 1 equal to omega naught equal to under root of in bracket g by l whole to the power 1 by 2, and omega 2 equal to omega naught square plus 2s by m power 1 by 2, and g by l plus 2s by m power 1 by 2 are normal mode frequencies. Okay. To simplify further displacement, let x naught equal to y naught equal to 2a and phi 1 equal to phi 2 equal to 0. Equation number 3 and 4 give equation 3 and 4 give capital X equal to small x plus y equal to 2a cos omega 1t. This is equation number 5, and capital Y equal to x minus y equal to 2a cos omega 2t. This is equation number 6. Adding 5 and 6 we get, adding 5 and 6 we get 2x equal to capital X plus y equal to 2a cos omega 1t plus 2a cos omega 2t. Small x equal to half capital X plus y equal to a cos omega 1t plus a cos omega 2t. Substituting equation number 6 from 5 we get subtracting equation number 6 from 5 we get y equal to small y equal to 1 by 2 capital X minus capital Y equal to a cos omega 1t minus a cos omega 2t. The corresponding velocities are given by differentiate of x equal to minus a omega 1 sine omega 1t minus a omega 2 sine omega 2 into t. Okay, and differentiate of y equal to that are velocities. Okay, equal to minus a omega 1 sine omega 1t plus a omega 2 sine omega 2t. Okay, now let the system be set in motion by displacing the bob x to the right by distance x equal to 2a, keeping y equal to 0, and both bobs are released from rest so that differentiate of x equal to differentiate of y equal to at a time 0 t equal to 0. The motion of pendulum is given by now let the system be set in motion by displacing the bob x to the right by displacement x equal to 2a, keeping y equal to 0, and both the bobs be released from rest so that x differentiate of x equal to differentiate of y equal to 0, because rest condition. Rest at a time t equal to 0. The motion of pendulum is given by the motion of a pendulum A is given by x equal to a cos omega 1t plus a cos omega 2t equal to 2a cos omega 2 minus omega 1 into t upon 2 into cos omega 1 plus omega t into t upon 2. And the motion of pendulum B is given by, and the motion of a pendulum B is given by y equal to a cos omega 1t minus a cos omega 2t equal to minus 2a sin omega 2 minus omega 1 into t upon 2 and sin omega 1 plus omega 2 into t upon 2. Okay, omega 2 minus omega 1 upon 2 is omega m is called modulated or beat frequencies. Okay, then omega 2 minus omega 1 upon 2 equal to omega m is called modulated or beat frequencies. Modulated or beat frequency. Omega 2 minus omega 1 upon 2 is called modulated or beat frequencies, and omega 1 plus omega 2 upon 2 equal to omega A equal to omega A is called average frequency. Average frequency. Okay. Omega 2 minus omega 1 upon 2 equal to omega m. That is modulated or beat frequency, and omega 1 plus omega 2 upon 2 is omega A, average frequency. Hence the modulated amplitude of pendulum. Hence the modulated amplitude of pendulum A equal to 2a cos omega m into t. Okay, and x equal to a cos omega a into t. Okay, the modulated amplitude of pendulum B, the modulated amplitude of a pendulum B equal to 2a sin omega m into t, and y equal to minus b sin a into t. Okay, and y equal to minus b sin a omega t, sin omega a t. Okay, then if we assume that the spring is very weak and does not store any energy, we can consider the modulated amplitude 2a cos omega mt and 2a sin omega mt to remain constant over one cycle of average frequency. Okay, energy of pendulum. Energy of a pendulum A equal to EA. EA equal to 1 upon 2 mv square, that is 1 upon 2 m a omega a square equal to 1 by 2 m 2a cos omega mt whole square omega a square equal to 2m a square omega a square cos square omega m into t. Okay, and energy of pendulum B. Energy of pendulum B equal to half mv square EB equal to half mv square equal to half mb omega a whole square, that is 1 by 2m 2a sine omega mt whole square omega a square omega a square that is 2m a square omega a square sine square omega m into t. Sine square omega m into t. Hence total energy E equal to EA plus EV equal to 2ma square omega a square. Evidently the total energy ET equal to EA plus EV. EA plus EV is constant as ma and omega are constant also. Okay, then EA minus EB equal to 2ma square omega a square cos square omega m into t minus sine square omega m into t. Okay, that is E cos 2 omega m into t equal to E cos omega 2 minus omega 1 into t. Okay, then EA equal to half E 1 plus cos omega 2 minus omega 1 into t, and EV equal to half E 1 minus cos omega 2 minus omega 1 into t. This shows that total energy is constant, but it flow back and forth between the pendulum and the modulus or beat frequency. Okay, this shows that total energy is constant, but it flows back and forth between the pendulums at the modulated or beat frequency. Okay, this shows that total energy is constant, but it flows back and forth between the pendulum at the modulated or beat frequency. Thus we see that after drawing aside the bob of the first pendulum by a distance 2a and releasing it, the pendulum shows the cosine behavior at a frequency omega a, which is the average of the two normal mode frequencies, and its amplitude also varies according to the cosine law at a low low frequency of half the difference between the normal mode frequency. On the other hand, pendulum second starts from zero and vibrates according to the sine law with the same average frequency, and its amplitude builds up to 2A and then decay according to sine law at same low frequency of half the difference between the normal mode frequency. The initial configuration, the initial configuration, the initial, the initial configuration, the initial configuration x equal to 2a and y equal to 0 can be decomposed into can be decomposed into capital X and capital Y modes. Capital X and capital Y modes are shown in the figure. The X mode is that X equal to Y equal to A, so that X not equal to X plus Y equal to 2A is known as in phase. In phase mode, and the Y mode is that X equal to A and Y equal to minus A, so that Y not equal to X minus Y equal to 2A is known as the out of phase. As the Y mode has a higher frequency, it will gain half a vibration phase difference pi radians on the X mode after the number of vibrations, and combination of X and Y mode then will give X equal to 0. Okay, X equal to 0. Then you can show also in this figure. Then if this is the first mode, and first Y equal to 0 and this is 2 and one number is this is one number pendulum, and this is X equal to 2A, and okay, X equal to 2A is equal to this is second position, and this is first position, and spring of second position is in initial condition is as like okay, Y equal to A and X equal to A. Okay, then this is okay, and okay, X equal to A, second position, equal to second position plus this is third position 2 and first, and this is normal condition, okay, this is normal condition, and the spring is as like this. Y equal to minus A and x equal to A. Okay, and in next condition, this is two position, this is one position, and one number is this is y equal to 2a and x equal to 0. Then okay, equal to 2 number position, first number position, and this is y equal to a, and this is second position. X equal to a, okay, and second position, first position, and this is as like, okay, and this is normal position, and in this x equal to minus a, and this is normal position, and y equal to a, okay. Then y equal to 2a as shown in the lower figure. Y equal to 2a after some times when y gains another half of vibration, x equal to 2a, and y equal to 0. Thus the pendulum only exchange energy the normal modes do not. The in phase mode remains in phase mode, and out of phase mode remains out of phase mode. Okay. Next type of coupling. Types of coupling. Two oscillators are coupled together to bring about an exchange of energy between them. The common coupling components for mechanical oscillators may be stiffness or mass, and in case of electrical oscillator it may be capacitance or inductance. Capacitance and inductance are energy storing electrical component, and coupling through them consumes no power, thereby making it possible for the energy transfer to make place over a number of oscillations. Coupling may also be done through the resistance component, but this causes inevitable loss of energy, so that amplitude goes on rapidly falling. Okay, the frequency of oscillation in phase and out of phase mode. Okay, and two oscillators are coupled together. Two oscillators are coupled together. Two oscillators are coupled together to bring about an exchange. Bring about an exchange of energy between them. The common coupling components for mechanical oscillators. The common Coupling components, the common coupling components, the common coupling components for mechanical oscillators, components for mechanical oscillators, mechanical oscillators may be stiffness or mass, may be stiffness or mass, and in case of electrical oscillators it may be electrical oscillators electrical oscillators, it may be capacitance or inductance, capacitance capacitance or inductance. uh, Capacitance and inductance are energy storing electrical components. Capacitance and capacitance and inductance are energy storing electrical components, are energy storing electrical components, energy storing electrical components, and coupling through them, and coupling through them consumes no power, consume no power, thereby making it possible for the energy possible for the energy transfer to take energy transfer to take place over a number of oscillations, take place take place over a number of oscillations, okay. Coupling may also be done through coupling may also done through the resistance component, but this causes an inevitable loss of energy, so that energy loss of energy so that the amplitude goes on rapidly falling, so that the amplitude goes on rapidly okay. Type of coupling. Two oscillators are coupled together to bring about an exchange of energy between them, okay. two oscillators are coupled together to bring about an exchange of energy between them. The common coupling components for mechanical oscillators may be stiffness or mass, and in case of electrical oscillators, it may be capacitance or inductance. Capacitance and inductance are energy storing electrical components and coupling through them consume no power, thereby making it possible for the energy transfer to take place over a number of oscillations. Coupling may also be done through the resistance component, but this causes causes an inevitable loss of energy, so that the amplitude goes on rapidly falling. Okay, next is frequency of oscillation. Frequency of oscillation in phase and out of phase mode. Okay, frequency of oscillations in phase and out of phase mode. The differential equation the differential equation of motion of coupled system of two identical mechanical oscillators, say two simple pendulum in terms of normal coordinates x and y, are given by equation of previous 7 and 8 are previous article. Double differentiate of x plus g by L capital X equal to double differentiate of x plus omega naught square x equal to 0, and double differentiate of y plus g by L plus 2s by m multiplied by y equal to double differentiate of y plus omega naught square plus 2s by m multiplied by y equal to 0. Okay, then where x equal to where capital X equal to small x plus y, and capital Y equal to x minus y, x and y being the displacement of the two mechanical oscillators. Okay, x and y being the displacement being the displacement of the two oscillators okay, two oscillators as the stiffness and m the mass, okay. First point, in phase mode, okay, in the phase mode x equal to y, so that capital Y equal to x minus y equal to 0. In such a case, the motion are completely represented by the equation double differentiate of x plus g by L into capital X equal to double differentiate of x plus omega naught square capital X equal to 0. The frequency of oscillation of the coupled system is therefore the frequency of oscillations of the coupled system is therefore omega naught equal to under root of g by L, okay, which is the same as that of coupled oscillators, oscillators, coupled oscillators. Okay. The frequency of oscillations of the coupled system is therefore omega naught equal to under root of G by L, which is the same as that of uncoupled oscillators. That is uncoupled. Uncoupled of oscillators. Uncoupled of oscillators. Thus in the in phase mode. Thus in the in phase mode. Thus in the in phase mode, thus in the in phase mode, the frequency of oscillations, the frequency of oscillations, the frequency of oscillations of the coupled system, of the coupled system, of the coupled system is the same as that of the uncoupled oscillators, same as that of the uncoupled oscillators. Uncoupled oscillators are of either pendulum in isolation. Okay. This is due to the fact that thus in the in phase mode the frequency of oscillations of the coupled system is the same as that of the uncoupled oscillators. Okay. Thus in the in phase mode the frequency of oscillations of the coupled system is the same as that of the uncoupled oscillators are either pendulum in isolation. This is due to the fact that the two pendulums are always oscillating in phase, as you can show our previous previous figure, so that the light spring always has its natural length. Second point. First point, show that the light spring, so that the light spring, always has its natural length. Second point, out of phase mode. Out of phase mode. Okay. Next point, out of phase mode. Okay. In the out of phase mode, x equal to minus y, so that capital X equal to small x plus y equal to 0. In such a case, the motion is completely represented by the equation and double derivative equation, and double derivative of y plus omega naught square plus 2s by m and to y equal to 0 out of phase. As much y equal to 0, show that x plus y equal to 0. In such a case, the motion are completely represented by the equation double differentiate of y plus omega naught square plus 2s by m into y equal to 0. Okay? The frequency of oscillations of the coupled system is therefore given by the frequency of oscillations of the coupled system is therefore given by omega dash equal to under root of omega naught square plus 2s by m, which is greater than omega naught, the frequency of uncoupled oscillators. The frequency of uncoupled oscillators. Okay. Thus, in the out of phase mode, the frequency of oscillations, of the coupled system gets raised. This is due to the fact that the two pendulums are always out of phase, either in the extended or in the compressed positions. You can show extreme position, and hence the coupling becomes effective. Extreme position raised, extreme position, hence the coupling becomes effective. Hence the coupling becomes effective. Coupling becomes effective. The extreme position, hence the coupling becomes effective. Thus, in the out of phase mode, the frequency of oscillations of the coupled system get raised. Okay, this is due to fact that two pendulums are always out of phase, either in the extended or in the compressed extreme position, and hence the coupling becomes effective. Okay, next, characteristics of in phase and out of phase modes of vibrations. Okay.